presentation on flight data monitoring?
Sure thing, Rex. So again, for those just joining, again, Cliff Johnson from the Tech Center. Again, helicopter safety, we're all on this call, from, oh, I'm sorry, it would help if I shared my screen. Apologies for that. Get used to having these systems up and you think everything's just going there, right? So again, FDM. And why does it matter? Well, right, we're trying to prevent accidents and incidents by more of a proactive safety, safety approach, right? We don't want to be reactive. FDM gives us the ability to try and monitor for trends and indicators and different things. Here's a slide of our team. Again, I won't go through everything other than to recognize Tyler, who's on the call with me here today. Been a big part of our group in the past and going forward. But we work with everybody. We work with HAI, Truth Data, Georgia Institute of Technology, from Pegasus. Alexia has done a lot of great work in this domain, and so has Paola, and everybody there. And then the folks at Rowan and others that we've been working on, of course, obviously the people at MITRE too that are our partners in some of this effort. Right, I showed the mission segments before, but I just point this out again, not calling one in particular, is that what we're trying to create with the work that we're doing for flight data monitoring is kind of these ideas of global events and things, right, that cut across mission segments, but then to dig into the specific segments as well, right? They have some unique events, exceedances, and concerns of their own over time. And we're very thankful, and we really appreciate all the people that have supported, our research and the ASIAS program to date. And it's definitely helped us, enhance and advance the work that we're doing. We wouldn't be anywhere near with the research that we're doing if it wasn't for the help of the operators in the community. For those that are not familiar, the helicopter safety team years ago had, and they continue to monitor it. We do the Paretos and everything. It really bucketed all the fatal accidents from, say, a 5-year period of time into one of these three top three areas, right? Loss of control, unintended or inadvertent IMC, and low altitude operations. And this has stood fairly consistent over the years. And then when you look at the mission segments, it's been more of like the personal private, the aerial application, and the commercial that really have had the bulk of the accidents, right? But there's been accidents in every category. So based upon that, with those three being the sort of the high water mark and where we need to, consider where the issues are at, we actually broke this out into a Pareto. And from that Pareto, we started to identify where are the safety metrics that we need to look at, which are the ones that are really going to get us the most bang for the buck, and how do we try to address those three, whether it's loss of control, inadvertent, or the low altitude. And we had started this a little bit before we had done that work with the USHST to identify the top three, but then we adjusted it to make sure. And it was good to know that we're kind of in that support. So again, when I talk safety metrics here, I'm referring to things that are more than just your typical exceedance or event. These are things that are a little bit more involved to monitor for. They may involve other data sets and other things that we have with the helicopter. So this is just a whole list of ones that we have, and I'll talk about some of them here during the presentation. The proximity to obstacles one was one that we looked at very early on, which identified obstacles and, just like it says, right, their location or proximity to the helicopter. So they're essentially, right, they're a hazard, right? So what's the hazard? How close are they? Are they no threat? Do they violate, separation criteria, potentially, right, up to something that you would see, and put that over through a map. We did the same thing looking at weather, and this was using something called the vertically integrated liquid, or VIL value. It was essentially our way of categorizing whether or not we went from, kind of like, no weather, clear skies, all the way up to like heavy rain and large hail. And again, the idea of putting this on something like showing with the flight path. The next thing I want to talk about, and I'll spend a little bit of time on, is really this metric of approach stability. And you just saw there with the, everything, you kind of saw, let me back it up here a little bit here and run it again. Let me see here. The green helicopter represents a stable approach path down to the helipad. Actually, that one probably goes over it, right? And but the orange and the red, right? They're kind of unstable, right? So how do you quantify that? It's really hard, right? Helicopters are different than airplanes. We all know that, right? They fly differently. And there's the glide slopes are different, right? Depending if you're a steep approach, shallow, or normal, right? So our approach to try and tackle this was, rather than set specific definitions or guidelines for the approaches and then seeing which ones fit into that or well, we tried to use some more of like those clustering type of techniques to quantify the stability, but leave it flexible so that it could account for those type of things, and then use statistical analysis and machine learning techniques to try and search for patterns in the data that identify unstable approaches, or at least the precursors to it, right? And we know if we're set up, if we're high, we're fast, that's probably going to be a bad thing, right? Or if we're low and slow. So those type of things as well. The process works very similar to what you saw with the ADS-B data, but with a caveat to it. So again, we're looking at flight data records. Those records contain takeoff, landing, and everything in between, right? So you have an en route phase, right? So we don't care about the departure phase for this particular metric. We only care about the approach. So how do we quantify that as well? So we have to detect that there's an approach there. So that goes into some algorithms that look to see, are we executing an approach? Are we descending? Number one, and then are we near a helipad or an airport, right, or a landing zone, scene, of different things, right? Does the approach have that characteristics? And then we split it by, is it a visual approach or is it an instrument approach, right? And we have different stability criteria for each, right? Yeah, I think somebody came on with, but that's all right. Stuff happens. So we have the visual. We go one direction, right? And we can't make it quite as tight as we do on the instrument. But the instrument, there's more steps to it, right? Because we've got to identify that it is an instrument procedure, right? Which IAP corresponds to that, right? Does it match? And then if it matches, right, can we perform the stability analysis on that, right? So we have this whole process. So again, showing that we start with the published approach plates. We look up the threshold location from the database. We had been putting this into a spreadsheet before. We worked to automate that since then. We read it into, like, for lack of better words, MATLAB, but we do some processing on it, right? And then we essentially build out these approaches. Now, we also pull the data from the coded instrument flight procedures database. So that's eliminated some of the intermediate steps, right? But we still have to kind of identify where are all the key information that we need to detect the approach, and then to see how well is that approach being flown, if you will, how stable is it? I shouldn't say well. It's not, because things can be unstable and it can be no fault of the pilot at all. It's just something that happens, right? So to extend upon that line of thinking a little bit, we didn't focus just at approaches. We started looking at holds and procedure turns as well, to be able to detect those in the data set. So that's part of it, right? So we look at how would we detect those, right? And the holding pattern, right? Is that being flown correctly and everything? But how, if we can identify a holding pattern, right, that may be another clue that we're at an IAF on the procedure turn, of an approach procedure, right? So that, here's an example of one, right? The ILS to runway 13 here at Atlantic City, right, where we have the the standoff distance here. Here's the ground track. Here's the distance to the waypoints. Here's the closure rate and everything that shows here. And then you can identify based upon these, I'm passing one of the fixes or different things. So, and in this case, it's a parallel entry that was shown into the holding pattern. So once we've got the approach down and detected, then we can start performing the stability analysis on this, right? So visual approach, we have some detection parameters, but we also do a little bit more when the code where we actually quantify the approach as, is it shallow, is it steep, is it an instrument approach, is it a missed approach, right? And you know, we go through different algorithms to be able to do that. Here's just some typical ones that are listed there. The other thing that we started to do with it is try to visualize it, right? So we have to consider the terrain, right? So we import that from one of the terrain databases. We bring in, you know, the heliport or the airport, and then we use that to estimate the AGL height, which is really important, right? Especially if we're going to a helipad that's not at ground level. The last thing that we start to do here as well is to add in the elevation and the azimuth. So essentially our localizer and glide slope to track what is that final approach performance, right? And we don't do that for the whole approach. We just do that when we get in close, essentially, right? When we're coming kind of either from the FAF or, you know, when we're, you know, sort of that base to final turn, right? And then, you know, the ideal approach, what we do is we construct what the ideal one would be based on if it's a normal, shallow, or steep, right? And then the best fit of what the flight path is. And then we calculate the deviations from that based upon the tracks that we see. And then you can do different metrics on there. You can look at like an average or standard deviation, you know, all those different things that come up there, right? You combine that whole process with classifying the data and doing data mining to find, you know, out, well, where are some of the outliers? And I know, you know, a couple of these ones that we looked at, some of these outliers were some of the FAA pilots, but we're not going to name names or anything on that. But some of the stuff we saw with our helicopter, and then other stuff that we've seen over the years. Again, it helps, right? This is how you go doing that, right? So beyond that, beyond approach detection and unstable approaches, right? I mentioned before loss of control was the #1 kind of fatality area, right? So it makes sense that you really want to target that. So how do you do it, right? Well, not every loss of control event is the same. They all have sort of different aspects to them, right? So we decided that we were going to go after like the major loss of control categories. So we looked at essentially starting out 3 things: auto rotations, dynamic rollover, and vortex ring state. But then we kind of moved into loss of tail rotor effectiveness, or what some people call unanticipated yaw. Again, looking what are the factors that influence LTE. And you know, Palazzanella, who I mentioned, is a grad student at Georgia Tech, she's doing her PhD thesis on this, and we worked to kind of come up with what are some of these risk levels for loss of tail rotor effectiveness, right, at a low level, high risk, and then getting into the event. The goal here was really to quantify and pick out events that could be indicative of a loss of tail rotor effectiveness approaching that in the flight data, right? Because that's what you want to see, right? You don't want to, I mean, it's one thing to analyze it after the incident or accidents happen, right? But you really, to make an intervention, you want to do this before, proactively, as part of your, you know, an effective safety management system. So that was our focus, was how do we detect these in flight? So we came back with sort of a graphic here that shows to the helicopter operator, you know, here's my helicopter, right? And then here's my events, what quadrants are they in, and, you know, what level were they at, essentially, with some statistical analysis here, some graphs and some other things based upon the flight. Again, if we know this information, we realize you may not have access to all this stuff depending upon what your helicopter is equipped with. The analysis process works based upon, you know, the lit review. We have some MATLAB code for the event detection, right? And then we've done some stuff in Flight Lab for monitoring and everything. And then we spit back the analysis results. We also use a BowTie model as well to identify, you know, what are the different threats, the barriers, the reactions, and the consequences that come out of this. And we've done this for more than just LTE, but I just wanted to show the LTE one kind of as an example of where we're going with this and what we used as a foundation. And then the other aspect of it has been really to look at, there's different models in the literature of aerodynamics between the main rotor and tail rotor interactions and how they're validated. Again, I'm not going to get into all the details on this, just to say that we're essentially looking at, the relative wind, where it's coming from, and the aerodynamics on the tail rotor, which help to enhance the metric. And here's another one you can kind of visualize. It's sometimes it's hard to see with these 3D type plots, but the idea here is, right, you're visualizing the effect that you're having, in the hover scenarios from an LTE event or something that approaches an LTE event. Similarly, and I'll just mention this one real briefly, has been kind of the work on vortex ring state. So again, with the modeling here, the objective of this one was slightly different. So we've done the same thing where we've tried to detect the VRS type of events or encounters in the flight data, and that's certainly a good starting point. But once you have that detected, right, what's the next step? Where do you go from there? So part of our effort really had been to compare the recovery techniques for VRS, and you have the two types, right? You have the traditional, right, and then you have the Richard recovery, which is basically the lateral recovery for getting out of this, right? So that equates to essentially 3 directions, right? You're not necessarily going to move backwards in VRS, right? You're more likely to pitch the nose over, try to get some forward speed, and get out of it straight ahead, or you're going to try to slide out of the vortex left and right. So how does that work, right? So we look at that. We look at based upon some initial conditions, and then we're basically studying the recovery time. And we did a lot of this work in the simulator, which is, they're not ideal in the way that some of them create VRS, right? They're working a whole nother project to try and see if we can improve some of the modeling of VRS, right? But it's good enough, right? It can get you some sense of where that occurs, right? And then potentially if you have some flight data as well, you can kind of evaluate the techniques, and then this can be another tool for the operator. Again, we're not recommending one over the other. They both have, I think, their pros and cons, and it really depends on the situation that you're in as far as what would really work best in the vehicle. We recognize that, but just to kind of do some statistical comparisons, because this is what kind of the industry had wanted to look at the time. And by doing that, we also have better detection capabilities for VRS as well. So this is just some preliminary stuff that we had found, where the yellow line essentially denotes where the encounter is, and it looks at what's your altitude, your speed, that steep descent and vertical speed, the airspeed, decaying there, and collective position cyclic. And again, you look at the altitude drop here and where the encounter shows up, because if it gets into that boundary condition, it's certainly an encounter, but it gets difficult to try to draw this curve for every helicopter and show that. So part of the challenge is how do you visualize some of these techniques for operators. So that's something we've looked at as well. So you see that there. The last thing I want to close with is just a mention of the ASIAS program. So as I mentioned before, this presentation is kind of focused a lot on helicopter flight data monitoring, but I'd be remiss if I didn't talk about ASIAS. And Stephen Dickerson and I were actually double booked, so he's taking another discussion right now, so he's probably not on one. But he asked me to pass along his, regards to the group. He's been, listening into the discussions the past 2 days as he can. But basically, as an update, what did we do in the past year? So we made some strides with ASIAS. The issue analysis team was formally incorporated and formed, and that's important because we have an analysis team for GA, the GA-IAT under the GA Joint Steering Committee. We have one for commercial, and that's where essentially the analyses are proposed and they're formulated, and folks go off and work the issues through the directed studies and different things. We also got formal incorporation into the ASIAS Executive Board through the helicopter safety team, The government and industry co-chairs are actually members of the executive board now, which is great. We didn't have that before. That's a very positive step for Rotorcraft. And then we completed the procedures and operations plan as well. And that document identifies and outlines the guidance for engagement with ASIAS, the governance, how we're going to bring data into the program, and how we're going to communicate our results and things out to the stakeholders and everything. And again, a big thanks to the people from AMOA, Sally, Sean, Ed, and all the folks that have been pushing to move this forward and have been helpful. HAI, who's been part of the IAT as well, with some of the calls and the folks at Truth Data. Everybody that's really been part of it. It's been great. We've gotten some participation from folks in the offshore sector as well. We continue to collaborate and communicate with Heli Offshore and HSAC, and again, all the other mission segments. Too many lists, but we really do appreciate everybody's work on this. And again, we're been working the research effort for several years and everything, and it's starting to mature now into an operational capability, which we're really excited about that. So we think we're going to get a lot of big things done in 2021. And you can see it from all the different talk that has happened with FDM right now. It's not a silver bullet, it's not going to solve anything, but it certainly is where the industry is going and where I think we need to go if we want to take the next step for improving safety. So with that said, that's all I had. And again, I will be happy to take any questions that the group has.
Thanks, Cliff. Excellent as always. We enjoy having Cliff on the U.S. helicopter safety team because he brings a level of technology and research that none of us have. I did get one question after your last brief from Joshua Dixon. He says, are there any projects in the works exploring the use of TISB, which traffic information system broadcast for the next gen, to create TCAS 2-level systems that would produce an RA? With the upgrade by avionics, many people had to pull the mode C-based transponders, and with it, TCAS 2.
Yeah, this one comes up a lot, Josh. I think it's an excellent point. I personally, I'm not aware of anything specifically, based on TISB to go to the level of a TCAS 2 system. But I think it's definitely needed for the reason that you've talked about. There is, as you know, there is capability within, the ADSB to provide the different traffic alerts, and people use that all the time, right? When I go on the ForeFlight, it'll give me traffic alerts when I'm flying and everything, right? But it's not an FAA certified, TCAS level 2 based system that would give me an RA. So I'm not aware of anything. Doesn't mean that it's not occurring. There might be, and I can certainly check and get back to the group here and everything. But certainly there has been some talk about modernizing TCAS, and I know there's work that's ongoing for new algorithms and things for collision avoidance for the next generation of TCAS, which is called ACAS, automated collision avoidance system. We've done some flight testing with that in the past at the tech center a couple of years back, but I'm not aware of anything with TCAS 2 specifically in regards to TISB.
Thanks, man.
Any other questions for the people online? Feel free to unmute and ask Cliff on anything that he's covered today. I do have one for you, Cliff. One of the things I was thinking about in looking at this is with the implementation of ADSB as well as the flight data monitoring system, looking at using FDM. I'm very familiar with flight data monitoring and have used it when I was overseeing pilots in the past. You can actually identify individual issues. You can also then identify group issues that may point to education and training. One of the things that we started to kind of look at was using it to identify site-specific issues as far as environmental. And you talked about Vortex ring state and stabilized approach. Are you working with combining ADS-B with flight data monitoring system in conjunction with weather? Basically overlaying and looking to see when pilots are being forced into a situation of a steep approach in a downwind situation that then would identify an environment that is a high risk. And then the next step, as we talked about before, is taking that and saying, oh, is that something that we can change? If we can't change that, should we implement an operational limitation? And also, should we look at that as a risk value and do a risk analysis that then goes into somebody's SMS system? And we can actually, affect a little bit of an impact on that end. I don't know, what do you think?
No, I think that's a great point, Rex. We had been looking at it from the perspective of, going inadvertent IMC, right? From mainly the conditions of, hey, you can get in the weather, right? I know we're working on a metric for that as a group. And then, the ones that I had shown before of sort of like, okay, there's severe weather here, and, how close did we come to it and everything. Hadn't really looked at it before from the perspective of, hey, like landing into, with a tailwind on a steep angle approach and everything. But I think that could be the next step of where we would take this, and, where we look at the studies based on, where the data is driving us. And I think this is something that I think everybody kind of struggles with. I have my thoughts on it, but where do we need to focus on? What are the types of analyses and things that we need to look at from the data? And one school of thought is to let the data drive you to those conclusions, and it will. But another thought is we come up with some of these scenarios or situations, right? How do we try to monitor for those and find those in the data set? In the idea of, hey, with that just culture paradigm that we all see. But I think what you talk about is kind of a natural extension of putting the weather piece together. And if we can, what's been missing in the past on that has been, what are kind of the local winds at the destination? If it's a heliport without an ASIAS or an AWAS system, right? I need to know what the ground, what the surface winds are doing, right? And maybe all I had before was that flag, for the windsock. But now I may not have that from the presentation that Gary and Walter and all the weather stuff that we heard yesterday, right? So if I have that data, available to me, absolutely, then I can, combine that with the other types of metrics, and we can really have something valuable to the group. So I think we'll talk more about it, but I definitely think that's a valid, thing that we could look at, and something we ought to pursue.